In this video, I will show you how to do heteroscedasticity in Stata. I have opened up the Stata program here and I have already executed it. So what we are going to be doing today is a graphical analysis of heteroscedasticity. Then I will talk about 3 heteroscedasticity tests, including the Breusch-Pagan test, the white test, and the alternative white test. I will then talk about corrections to heteroscedasticity, including robust standard errors, weighted least squares, and feasible generalized least squares. So before we get started, this is the data file that we're going to be using, and you will have to put this in the directory of where your data is going to be stored. So I highlighted and executed the whole program by just clicking on do, and these are the results here. So in the first set of analysis, what I will do is show you graphical analysis of heteroscedasticity. So here we have a data set on house prices. And so the dependent variable would be either house price in thousands of dollars or log of house price. And then we would have 3 independent variables, including lot size, which would be the size of the lot in square feet, square footage of the house, which will be the size of the house in square feet, and the number of bedrooms. These would be the 3 independent variables. We have 88 observations if we summarize the data. And then these are the means of different variables, standard deviations, min and max. And if we would like to list the data set, the first 10 observations of it, this is how the price variable looks like, again, in thousands of dollars. This is the log of price, and these are the 3 independent variables that we have here. So the first model that we would be running is regression model for price, and we would be doing regression of price on lot size, square footage, and bedrooms. And this is the output that we have here. And so again, we have several significant coefficients here for lot size and square footage. And that's how the results look like. Um, so in order for us to start with the graphical analysis of heteroscedasticity, the first thing we are going to do is predict. We're going to call this new variable u hat, and then comma residual is picking up the residuals from this regression. And then we would be doing graph two-way, and then the scatter graph of u hat against the square footage. So this is, I just picked up one of the independent variables, and we will be plotting the residuals against one of the independent variables. We can also plot the residuals against the fitted values, and this is doing with the RVF plot. Comma y line 0, and so that's what we're going to be plotting here. And then once we are doing this for the model of price on the independent variable, I will repeat the same analysis for the log of price. So if we regress the log of price on the 3 independent variables, I would call this residual u hat 1. So comma residuals, meaning pick up this residual. And then we would have the graph of residuals against the independent variables. So here we would be graphing two-way scatter diagram of the residual against the square footage. Again, I picked up this variable. And then we would be plotting the residuals against the fitted values from this regression here. So RVF plot comma y line 0 would be plotting these residuals against the fitted values. So I have actually executed all of these lines, and I saved the graphs and put them together, all 4 of them together. So this is the graphs that you will be getting here. And so this is the first one where we have the regression of price against, and then we calculated the residuals. So these are the residuals. And then we have the square footage variable. This is the independent variable here. This graph here shows, again, the square footage of that's one of the independent variables. And these are the residuals from the regression of log price. So this is the regression for price. This is the regression for log price. And if we're looking at the residuals against the fitted values, you kind of see almost like a similar picture. But here, instead of just one independent variable, we have the fitted values. This is the Y hat or the price hat. And that's what we see here. This is for price, and this is for log price, the results that we see here. So the reason we're looking at these graphs is we want to see graphical evidence of homoscedasticity or heteroscedasticity. So basically, we want to see if these residuals are increasing or decreasing in terms of um, one of the independent variables. So here we would see a lot more variation, and perhaps from visual representation, maybe we have the case of heteroscedasticity. Again, because here it seems to be kind of more narrow, here it seems to be more wide as far as the range of the residuals. We see more variance in the residuals. Whereas if we're dealing with log of price, we see kind of more everything is within a band, and so perhaps we would see the case of a constant variance here. But one thing is very clear: when you look at these graphs, it's very hard to tell which is the case of homoscedasticity and which one is the case of heteroscedasticity. Now, looking at the results later on, which I already know them, this is the case of heteroscedasticity, and this is the case of homoscedasticity for log price, and then we see heteroscedasticity in price. But it's kind of very difficult to establish this just by looking at the graphs. Okay, so moving on, let's now do several heteroscedasticity tests, and I will show you these tests here. So heteroscedasticity tests involve estimating the original model, regressing the squared residuals U hat squared on combination of independent variables, and then doing either an F-test or Lagrange multiplier test for joint coefficient significance. So we would be reading the same data set on house prices, and then I would be generating several variables. These include the squares of each of the independent variables. So for each independent variable, I calculate the lot size square, the square footage square, and the bedroom square. And then I would calculate the interactions between two variables like that we have here. So here we have heteroscedasticity tests for the model on price. So we would be regressing the price on the three independent variables, and then what we would do is we would predict the residual, and then we would call this U hat. Then we would generate a variable called U hat squared, and that would be the U hat to the power of 2 squares. And I would also generate predicted value y hat. I'm going to call it y hat, comma xb basically picks up the predicted or the fitted values. And then I would be generating a squared variable u hat, y hat squared, which is y hat to the power of 2. So for the Breusch-Pagan test, what it is doing, it's actually estimating a regression of u hat squared on the three independent variables. So u hat squared, that is the residuals of the original regression that are squared, and these are the three independent variables. So because we have three variables in this regression, I would be calling this k variable to be equal to 3. And then the goal here is the following. Now, if we have the case of homoscedasticity, we don't want this regression to be explaining anything, which means the coefficient should be not significant, and then the R-square should be very low. So let's see how these results look like. If we run the regression of price on the independent variables, this is what we see. And again, we have some significance in some of the coefficients. But again, this is the first regression. Then we are getting the residuals from this regression, squaring them, and then we get the predicted values squared. So the Breusch-Pagan test involves this regression here of u hat squared. So these are the residual squared from the previous regression. And here we have the three independent variables, and these are the coefficients that we have here. Now notice that we have this first coefficient. I'm looking at the p-value being less than 0.05. This coefficient here is significant, but the rest of the coefficients are not significant. I'm also looking at the r-square, and that's 0.16. So 16% of the variation in the squared residuals can be explained with the independent variables. So how do we do a more formal test? Well, we can do it with an F-test for joint significance of all the coefficients. So an F-test for overall significance is simply that actually the F statistic is listed right here. It's the 5.34, and the p-value is right here at 0.002. We can actually also calculate it using the F statistic, which is we pick up the r-square, which is this r-square here, 0.16, divided by k1. K1 was 3 independent variables. And then we have 1 minus the r-squared divided by n minus k minus 1. And so this would be the F statistic. 5.34 is exactly this one. And then the p-value, we're going to be using the ftail command that is picking up the degrees of freedom in the numerator, denominator, and this is basically the F statistic. And it's giving us the same p-value as here. So again, what we're finding here is because this p-value is less than 0.05, we have a case of heteroscedasticity. And we have that the independent variables jointly explain the squared residuals. We can alternatively use the LM statistic, which is n times the r square. So n is the number of observations, 88, times the r square is 0.16, and this would be the Lagrange multiplier statistic. And the p-value for that, because it's a chi-squared distribution, if we do a chi-2 tail, and we give it here the degrees of freedom, which is 3 in this case, and then the LM statistic, we would be getting this as the p-value. So again, using both the F statistic and LM statistic, we are concluding that we actually have heteroscedasticity in the price. So the next test that we would do here is very similar, which is the white test. And so for the white test, instead of just regressing y hat squared on the 3 independent variables, as we have the case here for the Breusch-Pagan test, we would also include this squares and then the interactions of the variables. And so here the number of independent variables would be 9 because we have 3 variables, 3 squares, and 3 interaction terms. So total of 9 independent variables. And here the way we calculate the F stat and the LM stat and the p-values is exactly the same. So let's look at the results here. When we estimate this regression with these 9 independent variables, I'm looking at which coefficients are significant. And actually here I only see one significant coefficient right here. The first one has a p-value of less than 0.05. The rest of the coefficients are not significant using a t-test. So using an F-test for overall significance, here is the F statistic, and this is the p-value. So we actually are finding that the coefficients are jointly significantly different from 0. And actually, if we're calculating the F statistic, here in the p-value, that's exactly the same as before. And the LM statistic is n, the number of observations, times the r squared. And here's the r squared is 0.38. And so this is what we get as a p-value for this test. So again, looking at this, we see one coefficient here was individually significant, but all of them are jointly significant using here this test, the F-test for overall significance of the regression. That's the same as here. And using the Lagrange multiplier test, we're also finding joint significance. So look again, this R square is relatively large as well. So the independent variables are jointly explaining the dependent variable. So the last form of test is the alternative white test. And what is different here is that we have a y hat squared regressed on y hat and u hat squared regressed on y hat and y hat squared. And these are the fitted values from the original regression of price on the three independent variables. So if you're looking actually at these tests, this really reminds us of the regression specification tests where we had the interaction terms and square terms. And here we have the fitted values of y hat and y hat squared. So it's very similar to that idea. So here we have two independent variables, and then we would be doing the F test and the LM test again for this for the alternative white test. So here, after we estimate this model, here we have y hat squared, and these are the independent variables. These are the coefficients. So we actually have two significant coefficients in here. And if you look at the F statistic and the p-value, we have an overall significance for this regression, and the R-square is 0.18. So we would be using the R-square, which is the N, which is 88 times the R-square. This will be the LM statistic, and that's the p-value for the LM statistic. So using the alternative Y test, we're also finding heteroscedasticity for the price equation, because again, we find joint significance of these coefficients. So here, our overall conclusion is that all tests shows for heteroscedasticity in price. Now let's repeat the whole thing very quickly for the log of price, and we would see what the results would show us there. So for the log of price, everything is the same that except for we regress the log of price on the three independent variables. We calculate the residuals, which is predict. I will call this u hat 1 to distinguish it from the previous residual, comma residual. We get the square residual, and then we predict the y hat 1 comma xb. These are the fitted values from this regression up here, and then we get the squares. Breusch-Pagan test again, we are regressing the squared residuals from this regression of the log of price on the other three independent variables, and we're displaying here the F test and the LM test. So this is the regression in log of price. And so if we do the Breusch-Pagan test, the regression for it, we would have the squared residuals on the three independent variables. So the squared residuals on the three independent variables. And actually, if we're looking at the p-values here, none of them are significant at the 5%. This one is significant at the 10%. So if we're looking at the F statistic and the p-value for it, we actually see that 0.32 is less than 0.05, which means that actually these variables are not, the coefficients are not jointly significant here. And likewise, the LM test statistic and the p-value is less than 0.05. So we are again concluding that we have homoscedasticity for the log of price, which means that the independent variables do not help explain these residual squared. So the next test that we would be doing is the white test, and the white test has several more terms, including the squared variables and the interaction terms. So if we are running this, this is the result that we would have. Looking at individual significance, I guess none of them are significant. So we could again test for overall significance. This is the test statistic, F statistic, and this is the p-value is greater than 0.05. So we don't have joint significance of these coefficients. And likewise, the LM statistic, the p-value for the LM test is 0.61, which means that it's greater than 0.05. And so again, we find that the coefficients are not jointly significant. So again, we find the case of homoscedasticity. The final test here is the alternative Y test, where we do the residuals squared from the regression of log price on the y hat 1. This is the predicted value for the log of price, and this is the predicted values for the log of price squared. And this is the regression that we have here that we would be doing. And we would see that these variables and the coefficients are not significantly different from zero individually. With a joint F test, this is the F statistic, and the p-value is greater than 0.05, so we do not find joint significance here. I've repeated these here as well. And then the LM statistic is the n times the r squared, so it's 88 times. You see, the r squared is extremely low, so it's less than, so 1% of the variation is explained by this regression. So the test statistic is very small, and the p-value is greater than 0.05. So again, we are concluding the case of homoscedasticity. So here, all tests shows for homoscedasticity of log price. So overall, the conclusion is that we found heteroscedasticity for price and homoscedasticity for log price. Therefore, we would be doing only corrections, heteroscedasticity corrections for the price equation. Okay, so the first correction that we would be doing here is heteroscedasticity robust standard errors. So many software packages, including Stata, calculate these. So how they're done is we would be regressing the price we on the three independent variables. And then if we want to do robust standard errors, we would have exactly the same regression, but we would add comma robust. And the comma robust calculates the robust standard errors. So if we look at the original model, it's this model for regression of price on the independent variable. And here, comma robust gives us the robust standard errors. So if you look at the coefficients are identical between these two models. What is different is the standard errors are just a little bit different. And actually, what you can find here is that the coefficient on lot size was significant here, but here it actually lost significance. So the standard error here, what it happened is actually it increased, so it made the coefficient not significant. And so but generally we do see the similar results in terms of significance for the rest of the coefficients. So when we are doing robust standard errors, again, the coefficients are going to be the same, and the standard errors are going to be a little bit different, which may lead to different significance. So let's go ahead and do the regression for log of price and then the robust standard errors for log of price. Now, we do not have to do this for the log of price because we found the case of homoscedasticity. So this is not necessary for the log of price because of the case of homoscedasticity. But let's see what happens if we actually correct in case when we don't need to. So these are the original coefficients that we have here. And these are actually the robust standard errors. And if I look at the test statistics, the t statistics, and the p-values here, we actually see very, very similar results. So of course the coefficients are identical because the robust standard errors just corrects for the standard errors. It doesn't correct anything for the coefficients. But the standard errors are here you see robust standard errors. They're very, very similar. So overall, the significance here is similar. So even if you apply robust standard errors in the case where you don't need it, then it doesn't change the results much. So the next thing we will be discussing here is the weighted least squares. And here's how we would be doing this. So This is for the case where the heteroscedasticity form is known. So let's assume that that's of the form the variance of u given x equals sigma squared times the square footage. So here I have assumed that the variance depends on the square footage variable. So in this case, we would be using WLS with weights that are 1 divided by the square footage, by this variable that multiplies the variance. Here we would be dividing by that. So how would we do a weighted least squares? This part is the same, regression of price on the three independent variables, and then we put in brackets a weight. A stands for analytical weight, equals 1 divided by the square footage. And this is basically how we would be doing these weights here. And when we estimate the model, this is what we would see here for the regression model. We would have regression of price on the other independent variables. Here is the analytical weight that we would have, which would be 1 divided by the square footage of the house. And if you look at the coefficients and standard errors, they would be actually different than the coefficients and standard errors of the original model after correction. So another way, this is the preferred way, of course, to implement weights, but another way in which we can implement it, we can divide each variable by the square root of the square footage. So here the weight was 1 divided by the square footage, but if we need to divide each variable by the square root of the variable. And so including the constant, so the constant would be 1 divided by the square root of this variable. And so we would call these variables stars here, the transform variables. The nice thing is that when we actually multiply the constant by 1 divided by the square root of this variable, what happens is that we have a case of homoscedasticity. So here we would be running regression, and these are our modified variables that we have here, where all of them are multiplied by 1 divided by the square root of the square footage. And then we would do common non-constant because the constant itself also has to be transformed. And so if we actually run this regression, if you remember these results, we would actually get exactly the same results here. Uh, and so look at this. The coefficients are exactly the same, and the standard errors are exactly the same. The only thing that's a bit different is just the R squared is a bit different between these two models. And this is because, again, we have here different sum of squares for these two models. So this is a more clumsy way to do things. So pretty much no one would do this, but we would definitely be estimating weighted least squares in this weight. So in this way. So notice that here, divide if the weight is 1 divided by the square footage, actually how we need to transform the variables are to multiply them times 1 divided by the square root of the square footage. And this is because of how we're doing here the weights. They're actually multiplying how they're multiplying the function when we are minimizing the sum of square residuals to get to the coefficients. So this is the case where we have a known form of heteroscedasticity. This is actually not very typical to know the form of the heteroscedasticity. So when we don't know it, we actually have to estimate it. So how we are going to be doing this is that we would assume that the variance of u given x would be sigma squared times, and here we would have this expression here, and I would have here exponent of this expression. So we would have this will be the expression, and I added the exponent there because we want to ensure that actually we have the case of positive variance. Otherwise, this expression could be positive or negative, and that we cannot have this for the variance. And here we just don't know the exact form, but for the heteroscedasticity, but we assume that it depends on these variables, and we would basically be estimating it. So we would be estimating h hat from here, and we would be using weighted least squares with the weight equal 1 divided by h hat. So let's estimate it first. How do we estimate it? We regress the price on the lot size, square footage in bedrooms. We predict the residual, and then what we would do is we would take the log of the squared residual for call it g. Then we would use a regression of g on the independent variables. We would be predicting the fitted values from here, and then we would be taking the exponent of these predicted values to get to h hat. So the reason why we're taking these logs and then we're taking the exponent is just to ensure that we would get the case of a positive variance. Otherwise, that would not be necessary. So now that we calculated these h hat, this will be now the same thing as our square footage variable from before. So we would be running a feasible generalized least squares, which would be regression of price on the three independent variables. And here the A weight, the analytical weight, would be equal to 1 divided by h hat. So when we estimate this, we would be getting these results here. For the coefficients and the standard errors. So here we have a little bit different coefficients and a little bit different standard errors from the model before, and these are the p-values, but overall similar results to the OLS, but these are again corrected for heteroscedasticity. Now we can do this the slow way, which is multiplying each variable by 1 divided by the square root of this h hat, including the constant. See, the constant also gets multiplied by this amount. And then we would be doing regression of these transformed variables that I just calculated before, right here. And then I would do non-constant because there's already a constant that I transformed in this model. And so these are the regression results that I have here. And again, we would be getting identical coefficients, identical standard errors as before. So this is why we would just be doing this if we don't know the form of heteroscedasticity and we want to calculate the feasible generalized least squares. We would just come up with this h hat correction factor and then use 1 divided by h hat as the regression. So overall, again, this is how to do heteroscedasticity tests. We are using the Breusch-Pagan white and alternative white tests. If we find heteroscedasticity, we definitely want to calculate robust standard errors at least, or we can move into WLS or feasible generalized least squares if we know the form of heteroscedasticity, and we could correct for heteroscedasticity that way. But overall, the results show that even after correcting for heteroscedasticity, the results are very similar in general. Okay, thank you for watching.